Some faculty outside. This is wait 1 more minute.
Yeah, sure, no worries. Oh, this is still on. Let me turn this off.
And this is Ohio State.
Ohio State University, yeah. Dr. Four. That might lead to some confusion.
Okay, we'll get started. Thank you everybody for joining us this week. So it's my pleasure to introduce you all to Dr. Brandon Paul. Brandon he's originally from Ohio, and he studied, he did his undergrad in music theory at Ohio State, followed it up with a master's in speech and hearing science at Ohio State as well. And then, if for those that don't know, he came here to do his PhD. Brandon and I actually started graduate school here at McMaster at the same time, 2012, I think it was. So it's really, this is exciting for me because this is my first time hosting a speaker, and to get to host somebody that I went to grad school with, I think it's pretty full circle and quite an honor. So Brandon did his PhD here with the late Larry Roberts, which many of you might remember. He did his PhD work on central and peripheral factors of tinnitus. Finished that up in 2016, moved up to a couple of postdocs, one at U Montreal and another at Sunnybrook Health Sciences, studying objective measures of tinnitus. He was telling me he's not really sure if they found them yet, so we'll see. And then in 2021, in the peak of the pandemic, he started, January 2021, he started his assistant professorship at Toronto Metropolitan, which was known as Ryerson back then. And there he studies brain changes after hearing loss, which we're going to hear about today. He's also recently started some collaborations with folks at Baycrest and at the Rotman Research Institute, working with folks like Claude Allain, looking at sort of cognitive factors related to hearing loss, and also looking at loneliness and social isolation and how that relates to hearing loss. So lots of interesting lines of work. Brandon and I, we started a soccer team when we were here together as PhD. I think we solidified our position as the worst team in the university.
We actually were. The Gold Diggers.
Gold Diggers. We dug no goals.
Yeah.
I think our first game we lost 18-0.
It was 14-0.
14-0.
Yeah,
Yeah,
don't
like
over-exaggerate.
Yeah. You stopped counting at some
Well,
point.
I may
Yeah.
have lost consciousness.
Yeah. Okay. Anyways, please welcome me in introducing Brandon Paul.
Good afternoon. Can everyone hear me okay? Audio good? Thanks, Ali, for the awesome introduction. It's really great to be back here in the PNDB department, and especially in this space where I was able to watch so many colloquia. It's good that you have a fresh coat of paint. It's a little bit brighter in here than when I was around. I'd like to put my acknowledgments, well, let me tell you what I'm talking about. First, we'll be mentioning one of the lines of work we have which concerns visual compensation and hearing loss. And this talk is going to be one of those that tries to raise more questions than it answers questions, and so some things are left unanswered, but that sort of is exciting to think about what directions we'll be moving. And I'd like to put my acknowledgement slide up front so I don't rush through these things at the end of a talk, but I'll be talking about two lines of research. They're related, but one of them stems from the time that I was a postdoc at Sunnybrook Health Sciences Center in their cochlear implant department there, and we still maintain an active collaboration, and I'll highlight Andrew Dmitrievich, who's here, whose work I'll be sharing with you today, and then another line of work which is related on age-related hearing loss with my own group, the Cognitive Hearing Lab at Toronto Met, and I'll highlight specifically the contributions of Patricia Aguiar and Michelle Williams, and just to note that this research is funded by NSERC. Before also moving on, I'd like to acknowledge and dedicate this talk to my late supervisor, Dr. Larry Roberts, who supervised me here in PNB from 2012 to 2016, and Larry tragically passed away in 2019. This is the last time I actually got to hang out with Larry, just a couple months before he died at the International Hearing Loss Conference at Niagara-on-the-Lake. And Larry is here. This is his wife, Marion, and also Phil Gander, who was one of Larry's students. He also graduated from this department in 2009. And I'd like the current students and maybe new faculty here to know how supportive and generous of a supervisor he was. He really bent over backwards to provide me with resources and guidance to succeed in this program and beyond. He always put me in front of doors of opportunity, and so many of my achievements are owed to him, and also in conjunction with Ian Bruce, who's here, who's also my co-supervisor at the time. It was with Larry, though, that I established pretty much the main theme of my research was how does the brain change after somebody loses their hearing? And that sort of operates as the platform for what we'll talk about today. We usually think about hearing loss as having these acute effects on speech perception, maybe awareness of acoustic events in the environment and so forth. But effects of hearing loss may extend beyond the auditory system to involve cognitive function and also how we use other senses. And that's sort of what I'll be mentioning today. So, the overview of what I want to talk about, first I would like to introduce everyone to the topics that sort of serves as the background. I'll be mentioning deafness, talking about neuroplasticity, and talking about visual behaviors in individuals who are deaf. I'm going to extend some of this research to talk about visual plasticity in speech outcomes in cochlear implant users, and sort of uses the deafness background as a basis for that. And then I'll talk about how, or whether, some of the things that matter for deafness and plasticity extend into a different form of hearing loss, age-related hearing loss, which is a little bit different from cases of complete deafness, and how those individuals may derive benefits from visual input in order to compensate for their hearing loss. So to begin, just some background on deafness and neuroplasticity. And there's this common view, sometimes established by popular media, sometimes in popular science, that as one of our senses declines, other sort of senses can become enhanced in order to fill in or to compensate for that. And this sort of invokes an idea of maybe superheroes like Daredevil who lose their sense of vision and all of a sudden they have amazing hearing and can feel the wind with their tactile sense. And we sort of have this idea that, yeah, all these other senses that we have that are intact compensate and they become enhanced in order to make up for that loss of auditory input. And while there is a kernel of truth to this, but it's far more nuanced than that may suggest. And I'd like to start first with the case of complete deafness, where someone is either born without any hearing or throughout, at some point in their life, they've lost the ability to hear completely. And so we might ask, well, what sort of visual behaviors are, if they are enhanced, what sort of behaviors are enhanced in individuals who are deaf? And there's a really helpful review paper from Carolyn Alencar, Blake Butler, Steve Lomber that has this nice table summarizing some of the results where we do have evidence where there are enhanced or supranormal visual functions compared to hearing controls. So things like motion detection, visual localization, visual motor synchronization, so synchronizing your movement to periodic visual stimuli, the acuity in your visual periphery seems to improve in individuals who are deaf, and also some evidence for object and face discrimination, even though there's some mixed results with respect to that. And so these are a list of studies where we do see enhanced visual abilities in deaf individuals compared to hearing controls, but it's not like every visual behavior improves. There is other things that it's not listed here, but I'll list them off for where there are no differences found between hearing individuals and deaf people, such as the perception of motion direction, motion velocity, discriminating visual events based upon their orientation, their timing, their brightness, contrast, color, acuity in foveal vision and the central vision. These things are no different in individuals who are deaf compared to hearing controls. So really it's not a wholesale change of improvement in your senses that are intact if you were to lose a sense. There are only some senses that seem to improve. And how we can come to better understand why that's the case is to understand maybe the underlying factors or changes to the nervous system that underlie these visual enhancements. And to motivate that idea, I'd like to introduce the concept of cross-modal plasticity, a form of neuroplasticity that involves changes to other senses after losing a primary sense. And so just to very oversimplify this a little bit, here is a typical hearing brain. We have normal input from the auditory system, and then we usually think about auditory stuff being processed in the temporal cortex and visual stuff being processed in the occipital lobe. Now, if someone were to lose their hearing, what we see is sort of an upregulation of visual activity in the auditory cortex following deafness. So the auditory system is no longer getting that input from the ear. What those neurons do is they start doing visual things. They start contributing to perhaps visual behaviors. And so this sort of idea of a recruitment of the auditory cortex after deafness may relate to the enhanced visual behaviors based upon research we know that has been done in animals. So we think that cross-modal plasticity has a causal role to play in these enhanced visual behaviors, and how we know that is by some research done by Steve Lomber and Andre Kral that was published in 2010, a really seminal paper. And so this research was done in deaf white cats. And so deaf cats are a very common animal model in cochlear implant research and in deafness research. And what we have here is a cat brain, and I'm not going to break down all these individual sections of auditory cortex, but these are different parts of the auditory cortex. You may recognize primary auditory cortex or the auditory core here in A1. And what they were trying to do in the study was to understand why these deaf cats had enhanced visual behaviors. And so the main question is, if auditory brain areas are performing these visual functions, then by stopping the function of those auditory regions, we should see changes or deficits in those visual abilities. So this is precisely what they did. In the cat auditory cortex, what they had done was to use cooling loops, so a way to temporarily deactivate different parts of the auditory cortex and then measure the resulting visual behaviors. The visual behaviors in question here are ones that are known to be enhanced in deaf cats, such as improved localization of visual events in the visual periphery, and also improved movement detection. And so what they did, and they tried a bunch of different areas, but what they found was they used these cooling loops, for example, to deactivate a part of the auditory cortex called the posterior auditory field. And what this did was introduced a deficit in the deaf cat's ability to localize visual events in the periphery, but this did not change movement detection. And if they deactivated the dorsal zone, or DZ here at the top of auditory cortex, they could introduce a deficit to the movement detection, but no deficit in the visual localization in the periphery. So this is sort of a classic double dissociation, suggesting that these visual functions are related, causally related to brain plasticity that goes on in the auditory cortex. So the auditory cortex is contributing to these visual functions. So this idea of how the auditory cortex changes as it's recruited to do visual functions is interesting to us because it may have implications for individuals who restore their hearing with a cochlear implant. And so we're going to move on to talk about the research of how we're going to apply these sort of ideas to better understand speech outcomes in cochlear implant users. The main question we want to ask here is that, sure, if we have these auditory neurons that used to do auditory things, then deafness comes, and now these auditory neurons are doing visual functions. What happens if we turn the auditory system back on using a cochlear implant? Those auditory neurons that are doing visual things, can they convert back to doing auditory things to support speech perception? And that's sort of an interesting debate to talk about. Sort of as a background of what a cochlear implant is and how it works, just very briefly, if this is a new concept. So individuals who either have profound hearing loss or who are completely deaf can opt to get, well, in some cases can opt to get a surgery in order to restore their hearing with an implantable device. And how this sort of works is there's an electrode array that can be directly implanted into the cochlea itself. And those electrode array, what it does is it delivers electrical pulses right to the auditory nerve itself. And this direct stimulation of the auditory nerve can give rise to the sensation of sound. And what happens is that for the CI, there's a sort of an earpiece that hangs out behind the ear with a microphone on it. The microphone picks up sounds, such as speech. And then a processor, what it does, it sends these signals to a receiver on the inside, which then sends that information directly to the electrode array. And so what this kind of looks like is if we take like a sound waveform, and what it does is it creates these electrical pulses that are shaped just like the speech itself. And upon implantation, and with a little bit of rehabilitation, a person can start to recognize these speech signals and even use them to communicate pretty well in daily life. So it's a really cool technology. It's the most successful neuroprosthesis that we have. But one issue with it is, even though it sounds really cool and it works well, is that it works really well for some individuals and doesn't work as good for other individuals. And one of our mandates in the cochlear implant program when I was there at Sunnybrook was to figure out how can we improve speech recovery or speech rehabilitation, and what sort of factors go into that. And why a person with a cochlear implant would do really well, and maybe they get the implant, they are able to communicate within a couple days or a couple weeks, and then they have a really good quality of life. Some individuals, it takes them weeks, months, or even years, or don't even reach levels of what we would call great speech perception even after receiving the device. And so why would someone have either good or bad speech perception after having a CI? And there are a lot of factors that go into this. I'm not going to describe specifically this graph here, but a lot of things are determinants of speech recovery with a CI, such as what caused the deafness or hearing loss, the etiology, the duration of deafness, how long they were deaf, how old they were when deafness was onset. Were they born deaf, or did they acquire deafness later in life? And how old were they when they got the implant relative to the time that they became deaf? Excuse me. So all of these factors do play into whether or not someone has good or not so good speech recovery, but there are other factors at play that are quite interesting. Those might be neural factors such as brain plasticity or someone's capacity to learn. And so how this relates back to visual cross-modal plasticity is that one of the factors that has been historically strongly correlated with speech outcomes is this idea of visual cross-modal plasticity. And that's sort of where it brings us back to the topic at hand. The main debate, it seems to be raging right now in the cochlear implant world, is whether or not this cross-modal plasticity is beneficial or detrimental. So again, just to think of the idea, if you have these auditory cortical neurons which are no longer getting input from the ear, they become recruited to do visual functions. Are those neurons now doing visual functions unavailable to support speech perception if you turn the auditory cortex back on with a cochlear implant? And there's sort of two views about this and two lines of evidence that have been contrasting. So to graphically describe what I mean here is that if we have a person before receiving a cochlear implant, so pre-CI condition, then we have visual activity going on in the auditory cortex. After they get a cochlear implant, those neurons, again, they may be busy doing visual things, and once the auditory system is reafferented, then there may be some sort of competition for resources in this area that sort of disrupts the ability for individuals to have adequate speech recovery. And there's a lot of lines of evidence for this. Originally, it was this Lee et al. Paper in 2001 published in Nature finding that individuals who had a lot of activity going on in the auditory cortex related to visual processing, after they got a cochlear implant, individuals with more of that visual activity had worse speech outcomes. And so this sort of sets up a competition view. And there are several papers that do this. Most of these papers, how they operate is they present visual stimuli to a person who is deaf. They measure the activity coming from auditory cortex, and cross-sectionally they just correlate that with speech recovery scores. And so this has been an evidence basis to say that, you know what, this visual cross-modal plasticity is bad. Maybe we need to do things like limit visual behaviors. Don't use sign language. Don't read lips. And if you intend to get a cochlear implant, we don't want that visual plasticity taking over auditory cortex. But there's a competing line of evidence, fewer papers, but one I'd like to highlight here is by Carly Anderson and colleagues in 2017, suggesting rather a cooperation view. And what this research had done was to look at cochlear implant users after they receive their CI and measure the amount of cross-modal activity that happens, so visual activation of auditory cortex, and they were using real speech stimuli to do this, and they find the opposite. Individuals who have more of this cross-modal activation actually have better speech scores. So maybe instead of thinking about these neurons competing for resources, if we look at stimulus processing related to visual speech that's relevant for what they're trying to do, there's a lot of redundancies in the visual speech signal that can help us resolve maybe some of the uncertainty in the auditory signal that's coming up from the periphery where someone's relearning to understand these degraded speech sounds that eventually become something that is useful for their daily communication. So there's this cooperation and competition view that sort of needs resolution because and to understand this is quite important because we're dealing with somebody's livelihood here. This is their quality of life of using this device. They went through very expensive surgery, a long recovery time. If we're making these decisions about whether or not they should be using visual language, it has massive effects for the rest of their life, to be honest. So we need to resolve these things in order to dictate the best course of rehabilitation for individuals who are cochlear implant users. And so we wanted to drill down on this more to understand, in this first study I'll talk about, how visual stimulus processing and how that relates to cross-modal activation correlates to speech recovery in cochlear implant users. So this first study, and I'm highlighting Andrew Dmitrievich down here, with whom I worked on this project. This paper came out a couple years ago. What we wanted to do was to use, and previously a lot of the stimuli that were used to look at cross-modal activation were things like moving checkerboards or random dot patterns that can evoke visual activity, and we can measure that from auditory cortex. But we're more interested in using perhaps ecologically valid stimuli or speech-relevant stimuli, because that might tell us something better about what those neurons are doing in order to either compete with or cooperate with auditory speech. And so we have a really basic task, which is sort of a lip reading study where we present the lower half of a face here as a video, and this is an individual speaking a monosyllabic word. I think it's bass is what he's saying here.
I saw bats.
Bats? Wonder why. Curious. We should, anyway. So once again, so we're presenting the stimulus it's a very simple stimulus, and what will happen here is that when we present the stimulus, and if we record brain activity, I'll talk about this in a second. If we record brain activity using EEG, when the video is first presented, this is going to create a brain response. There's going to be a visual event there, and we can see what is the brain doing as it responds to the onset of this video. So the brain response to the onset of the video is one sort of feature that we're looking at with respect to the brain activity. And also what we're going to do is to look at ongoing neural rhythms or neural oscillations as somebody is observing this lip reading video. And so instead of I'll go back to the stimulus itself. So if the onset of the stimulus is one thing, then as they're watching the video during this time period, the brain is processing what's going on there, and what we're going to do is we're going to look at neural oscillations that happen during that time. And we wanted to do this because we wanted to compare different forms of visual stimulus processing as they relate to these speech outcomes. And we had done this in this study with 15 postlingually deafened CI users. What that means is these are CI users who acquired deafness after developing language, and then we're testing them 1 year after their cochlear implant was activated, and we're comparing them to 13 age-matched controls. And so already you might be saying, those aren't very large sample sizes. And I would agree with you, but here's the thing. Cochlear implant users, relatively rare. At Sunnybrook, we only track 2,000 of them, only a fraction of whom like to participate in studies. There's only about 1 million cochlear implant users worldwide. In the cochlear implant world, that's considered a large sample size. Usually we're operating between 6 and 9 individuals, so we're actually quite happy with this. But reservations about adequately powered samples aside, I can appreciate that comment. So very simple task. We present this lip reading video, and we do collect behavioral responses. The participant types their response on a computer screen. What did you see? We actually didn't find any differences in the cochlear implant users and the typical hearing controls in this study. We would expect to find that. Many other studies do find improved lip reading ability in cochlear implant users, but we didn't happen to find it in this study. Maybe it was the type of stimuli we were using. I'm not going to talk too much about that. So yeah, we measure 64-channel EEG while participant observes these videos. And then also what we're going to do is compare those brain responses to a standardized speech test that's commonly used in the cochlear implant world, which is the AZ Bio Sentences and Noise. What this means is that this is a speech and noise test, so there's some sort of speech sentence or word that they have to listen to, and they just simply report back what they hear, and then what we can do is put in some background noise. And what 5 dB SNR means is that the level of the background noise is 5 dB below the level of the speech signal. So it's possible for CI users to do this, but sometimes it's hard, sometimes it's easy, depending on the individual. All right, so let's launch into some of the results and data here from what we found. Just as showing a demonstration of this cross-modal activation that we typically see. So what we do is we use source analysis to try to estimate the level of activity coming from auditory cortex. And so what we have is the activation we see for cochlear implant users in red and in typical hearing in blue. And you can see there's a little bit more activity happening along the superior temporal cortex in the CI users. And if we look at the time course of that activity, after the onset of the video, so this is the video turns on, there's going to be a brain response. And we can source the brain response to estimate how much activity is coming from auditory cortical regions. And CI users have larger responses compared to typical hearing controls. This is not remarkable. This is reliably seen across different studies. It suggests that there has been sort of some form of cross-modal plasticity, and this higher amount of activation would be indicative of that. So that's not too surprising. What people haven't looked at, however, is another form of stimulus processing. So what is the brain doing as it's observing that lip reading video? And to do this, we're going to look at neural oscillations. And so I'll show you these spectrograms for both the normal hearing controls and the cochlear implant users. And just to orient you, here on the x-axis we have time. So the video is about 2.5, 3 seconds long, and so this is the duration that it's going on. And I'm highlighting the time period for what's happening in the video. On the y-axis is the frequency of these neural oscillations from 5 to 15 hertz for both normal hearing and CI users. And what the color represents is the change in the strength or the power of these neural oscillations relative to baseline. So reddish colors mean an increase in the power of these brain rhythms, and blue colors mean a decrease in the power of these brain rhythms. And we already see descriptively, interestingly, from these spectrograms here, for normal hearing individuals, we see much more of a decrease in these brain rhythms between frequencies of about 8 to 12 hertz as they're observing the lip reading video. And the CI users, they don't have as strong of that decrease in that power. And so what these 8 to 12 hertz brain rhythms are, we usually refer this as the alpha band. So from henceforth, I'll be talking about this as alpha rhythms or alpha activity. And to better understand this, if we look at these individual differences between normal hearing and CI users, as we source this information to auditory cortex, we see something interesting. Normal hearing controls here pretty much almost always show the same configuration of results, which is a decrease in the power of these alpha rhythms. But what CI users have is actually quite a lot of individual variability. Some people do have decreases in this alpha power, while some have increases in this alpha power. So that's kind of interesting. Is that difference relevant at all for speech communication? And that's sort of what we want to go on to next. So we're able to quantify these sort of different types of visual stimulus processing that goes on, whether it's the onset of the video or whether it's neural oscillations during lip reading. And then what we want to do is correlate these things to their speech scores that I had mentioned before. So let's take a look at those things, and maybe we can unpack this a bit. So this is the correlation that we find for our CI users. What we have on the x-axis here is the onset response magnitude, so larger values mean a bigger response. And on the y-axis, we have their speech and noise scores, that AZ Bio test that I had mentioned a while ago. And what we see is a positive correlation. Those individuals who had bigger responses actually have better speech and noise scores. Oh, interesting. That would be consistent with a cooperation viewpoint. So plasticity maybe is good for speech recovery in these individuals. So that's one thing. But then let's also look at the alpha rhythms as they're watching the lip movement. The opposite. Those individuals who have increases in the alpha power during the lip reading time of watching the video are those individuals who have worse speech and noise scores. And remember, the individuals who were control subjects, they tend to have decreases or negative values for these alpha rhythms. So those individuals who have brain rhythms that more resemble the normal hearing controls are the ones who have better speech scores. So looking at this in isolation, it would be suggestive of a competition viewpoint. More of this cross-modal activation is maybe not so well related to good hearing outcomes. And so this is an interesting thing to us because it maybe suggests that this cooperation competition idea is somewhat oversimplified. Maybe whether or not cross-modal activation is good depends on the nature of the stimulus processing, whether here we're only showing the onset response versus brain oscillations that are going on as they're observing a lip reading video. But I think the story is more complicated than saying whether cross-modal activity is good or bad. In order to try to help us understand this situation a little bit better, we endeavored on a second study in order to test cochlear implant users preoperatively. So before, those individuals that I had just mentioned, they received their CI, and then we tested them completely 1 year after activation. Well, what do these brain responses look like before they receive a cochlear implant? And then we can compare that brain activity to speech scores later on. So here comes the messy caveat stuff. This study was started during the pandemic and had intended to be a longitudinal study because that would be the best way in order to understand how plasticity is changing from before and after. Well, pandemic interrupted our data collection and we could only test individuals before they received their CI, but we couldn't test them a year afterwards. So again, we're going to be looking at things cross-sectionally, but maybe it can be informative to see whether or not we see the same or different configuration of results. We are doing this longitudinally now in a new study, but I don't have those data available for you. I apologize. So from these new data that we have, we reanalyzed our 2022 data that was published based on some comments that we had from, not from reviewers, but from colleagues, we analyzed the brain data a little bit different way to see whether or not the results were robust, whether or not they were a consequence of how we were analyzing the data. It didn't change anything, but the configuration of data will look a little bit different qualitatively. So we were also looking at different parts of auditory cortex, but we're not going to talk about those results today. But we can compare the brain activation to the onset of the video here on the graph on the screen across the normal hearing, the cochlear implant users we had seen before in red, and now our new group, the cochlear implant users tested preoperatively. And again, nothing surprising, especially with the pre-CI users. They have much larger brain responses to the onset of those videos compared to normal hearing controls, and also larger compared to the cochlear implant users tested 1 year after. And also, if we look at the brain oscillations coming from auditory cortex for the lip movement, also same kind of thing. Same results as before for the normal hearing controls and the CI users, but also in the pre-CI users, we see this mixture. Some individuals have increases in the power of alpha oscillations during the observation of lip movement, and some have decreases. So that's cool. Let's look at the correlations to brain activity. So nothing new here. It's a different looking correlation, but it's the same data as before. Positive correlation between the speech and noise scores and the movie onset responses themselves. Now, if we look at the pre-CI users, the opposite. Those individuals with larger brain responses actually were, later on when tested, had worse speech outcomes. So it tells us already these are sort of conflicting results. So this to me, what I draw from this, and it's sort of tempered by the idea that we don't have longitudinal data, is that it's less about looking at these results cross-sectionally, and more studies need to look longitudinally. How or whether brain plasticity changes before and after, I should say visual brain plasticity changes before and after receiving a cochlear implant is what we actually need to track here. I think looking at these things cross-sectionally, looking at these individual differences isn't revealing to us the complete story. And so the conclusion I'm leaving you with here is that this cooperation and competition view might be a little bit oversimplified, at least from when we look at these onset responses and how they relate to speech recovery scores. So what about the alpha power, the alpha oscillations while somebody's observing lip movement? Here's the same data as before, this negative correlation between alpha responses and speech and noise scores. And then when we look at the CI users who were tested preoperatively here in yellow, we actually see the same configuration. Those individuals who tended to have an increase in power, in alpha power as they watch this lip reading video, have worse speech and noise scores. And this is more interesting because it suggests that maybe is a stable sort of thing that we can look at. We still should look at things longitudinally instead of cross-sectionally. But this could be interesting that lip reading alpha rhythms may be predictive of speech outcomes. And if this is something that is robustly the case, then we can maybe use that sort of brain activity to predict how well someone will do with their cochlear implant. More work needs to be done on that. The thing is, I'm not quite sure what those alpha rhythms represent. There aren't many studies or any studies that I'm aware of that have looked at brain oscillations while somebody is engaged in lip reading, let alone if you try to estimate the contribution of these cortical sources to the auditory cortex. I should say that these correlations that we have on the screen here, they don't correlate with any activity coming from the visual system. And I had neglected to mention, but I'll mention it now, is that cross-modal plasticity isn't the only outcome from deafness. There's also something called intramodal plasticity. So the connections within the visual system itself can strengthen as a consequence of losing another sense. And so intramodal and cross-modal plasticity may reflect the same or different mechanisms, but here we did not find any correlations between brain activity coming from the visual cortex and these speech outcomes, only to brain activity that we estimate to be coming from auditory cortex. So the take-home points that I'd like to leave you with, at least this first half of the talk here, is that the relationship of visual cross-modal activation to CI users' speech outcomes may depend on the type of visual stimulus processing. You see a little bit different results from the onset responses compared to the brain activity ongoing while somebody is observing lip movement. This alpha activity might be a novel response to explore further, and whether or not it's relevant to speech ability in hearing loss and in deafness. Maybe it tells us something about how people are leveraging or using visual information in order to maybe compensate for the fact that hearing is still difficult. A lot of this is quite speculative, but more work needs to be done on that. And finally, a point that I've made a few times here is that longitudinal studies are definitely required to track the evolution of visual plasticity in CI users. So that's kind of where we've left off. Stay tuned for more research on that, but specifically I'd like to nail home the point that this cooperation competition viewpoint I think is maybe too simple to explain to all the results that we have out there, but how plasticity is unfolding as somebody lives their life with deafness and what happens after they receive the cochlear implant is required to better understand how speech outcomes could be affected. Cool. So I'd like to now, and I think we're well on track to transition to the second half of the data that we'll talk about today. So we're going to leave Sunnybrook and we're going to come back to Toronto Metropolitan University in my own lab, where the main question is do these principles of visual plasticity that I'm talking about extend into another form of hearing loss called age-related hearing loss? And I'd like to talk a little bit about some main differences between age-related hearing loss and the deafness cases we were looking at before. So before we were talking about almost complete or almost nearly complete or totally complete deafness, where you're almost disconnecting the ear from the brain. In age-related hearing loss, that's not the case. Hearing loss progresses gradually, begins around the age of 40. Definitely, people above the age of 70, most of them have some form of measurable hearing loss. And it can happen, but not so often is total loss of hearing. But mostly what we're dealing with here is sort of partial hearing loss, where there's still some sort of afferent connection from the ear to the brain. And that there's still some sort of drive onto auditory cortex. And so the question is whether these similar visual plastic effects that we had mentioned in CI users and in deaf individuals, do we find the same thing in age-related hearing loss? And are those things relevant for speech perception is a secondary question. Also with age-related hearing loss, we're dealing with the factor of age. And so often we need to be very careful about what are aging effects that are separate from sensory loss. And many studies actually, and I'll talk about this in behavior results in a little while, but many do not tend to wrestle with these two dimensions. So anyway, the first question is, all right, we see this visual plasticity in CI users and in deaf individuals. Do we see the same thing in age-related hearing loss? And so what evidence do we have that exists for this? There's not a lot of studies. There's only two that I can tell you about, and I'll highlight one here from Julie Campbell and Anu Sharma, published in 2014. So again, the main question here is, do we see some sort of changes in visual brain responses as a function of declining hearing? I'm going to be a little bit more agnostic about whether things are cross-modal or not, or intramodal or not in this part of the study, because these studies do not try to estimate different cortical sources. So I'm going to be talking about these things generally as visual plasticity. Whether or not they're cross-modal or intramodal is less important, more so than seeing if there are differences in visual brain responses that correlate to the level of hearing loss somebody has. So in this Julie Campbell and Anu Sharma study published in 2014, they used a stimulus that kind of looks like this. Is this going to work? No. It works when I don't have this in presenter view. Let me advance a slide. What it is it's two alternating frames. It looks like this circle pattern and this star pattern. And what that gives us is these things flash every about 600 milliseconds or so. They alternate between these frames, and it gives rise to the perception of apparent motion. So it looks like this circle is sort of collapsing into a star, and then it grows out to a circle again. It's circle, star, circle, star. Later on, if you're actually curious about seeing it, if I'm not in presenter view. Should we do that? It's really not super spectacular, but let's see.
You have to have screen mirroring on her.
Whatever, yeah, we'll do it this way. Looks like that.
There we go.
Going to hide my laundry. So you kind of see that? That's sort of the stimulus that's being presented. Let's bring it over here. Thanks, Paul. Link this back up again. So the general idea of why the stimulus is being used here, oh, frickin'. The general idea of why this is being used was this sort of stimulus was developed in deaf individuals to examine visual brain responses as well. And so Julie Campbell and Anu Sharma, that they tried to apply this to individuals with mild to moderate hearing loss. And that's what they had done. They had groups, two groups, those who had typical hearing ability and those who had mild to moderate hearing loss. And I'll talk a little bit later on about how you measure that. But the main idea is, like, what do the visual brain responses look like? And we'll be looking at typical looking visual evoked potentials in this sort of depiction here. And here's what they look like as compared between the two groups. The main finding here is that, let me turn my pointer back on. Those individuals who have mild to moderate hearing loss, they have larger amplitudes for this brain response, and they have earlier latencies, so faster brain responses compared to a typical hearing control group. Oh, cool. And so most of these results are focused on the N1 potential, and just to highlight, that looks like right here, this negative going voltage activity that happens 200 milliseconds or so after the stimulus changes. So every time the stimulus changes, then about 200 milliseconds afterwards, we can see this nice negativity that is indicative of visual stimulus processing. So the main idea that we're looking for here that was very influential for us is, hey, are these larger and earlier brain potentials something that can be a marker of visual plasticity? This would be consistent with some sort of visual changes ongoing, whether or not it's intramodal plasticity or whether or not it's cross-modal plasticity. And if that's the case, maybe we can try to understand differences in these brain potentials. And that was sort of the impetus for the study that we wanted to do, was to try to replicate and extend that result, because maybe we can use this visual plastic response as some sort of marker of training or a recovery of speech ability later on. So the goal in study 3 here was to replicate that Campbell and Sharma paper, but also to extend this to a stimulus that maybe is a little bit more relevant to speech. And so what we have here is to compare to the circle star stimulus, and I don't have an animation for the mouth opening and closing, is this sort of cartoon mouth that sort of alternates between two frames. It's a little bit terrifying to look at, and there are other forms of this, of other phonemes that look even more terrifying. The teeth look like the mouth of Sauron from Lord of the Rings films. It's really kind of terrifying. But anyway, we like this sort of stimulus too, because we needed two alternating frames in order to match the number of stimuli that we're presenting and also constrain things within a certain degree of visual angle. And, but it has a little bit more relevance to speech. Somebody could be imagining, or somebody could be thinking about somebody making an utterance there that you're not quite getting from the circle stimulus. So we had presented both of these stimulus sets in a much larger sample than before. In that Campbell and Sharma paper, there was a total sample size of 19 individuals, and we wanted to power that up. And so these are the numbers that I'm typically used to in my lab. So we have 69 individuals participating in the study, age range from 53 to 80 years, average age of 70. We have 40 women and 29 men as self-reported. And so the numbers here, if you're not in the hearing world, I'm sorry, this is a bit complicated, but we're measuring their thresholds, their auditory thresholds as a measurement of hearing loss. And so what this means is that we're averaging their pure tone thresholds from 2 to 8 kilohertz across both ears. And the range that we find across our participants is between 9 and 74 decibels hearing level. And we would typically think of hearing loss as being values above 25 dBHL. I mean, it depends on who you're talking to. But what this represents is a good variability that we're interested in this sample. So some people with lots of age-related hearing loss and some people with not so much age-related hearing. So really good hearing relative to their age. Nobody was using any devices, so this is all untreated forms of hearing loss. No hearing aids, no cochlear implants. And then we compared these two stimulus sets while we recorded 64-channel EEG. All right, so just a refresher on what we are looking for is a brain response that kind of looks like this. And we do find that something very similar for our two stimuli here. So just to orient you, the orange color is the sort of lip reading stimulus or the lip motion stimulus that we made, and the green colors are the circle stimulus. Here across time, we're looking at the amplitude changes coming from EEG sensors across occipital regions. So these are where these responses are reaching their amplitude maximum. So this looks like your normal visual evoked potential. Nothing's too surprising here. What I don't understand, maybe someone who's more of a visual expert can tell me. I don't know what this early negativity is for that lip reading stimulus. You can talk to me after, or you can ask it in a question, but mostly we're going to be focusing on that N1 response, which was the one that originally was reported in that Campbell and Sharma paper. I'm going to depict some data and some analyses using some simple correlations, but I want to tell you that the way we analyze these data is using linear mixed effects models. So how we draw our inferences and what conclusions I'll make will be it'll be qualitatively same as what I show on the screen here, but how we draw our inferences is not from simple correlations, and because we try to account for other variables as we make these measurements. And
is this the average of both the mouth opening and mouth closing? Like 0
Yeah.
there is both closing and opening?
that's right. All either both the circle star and the mouth opening are, yep, yeah. We haven't looked at it.
Have you looked at them separately?
We haven't, but that's a great idea. Maybe we will. Mostly we had done that to get it accurate, like to get it to get a good signal-to-noise ratio. There are 500, so there are 250 presentations of either opening or closing, so 500 total presentations of either. for both of those things. But yeah, probably we might see some differences.
The duration, you said, of the stimulus itself?
600 milliseconds between each change, and they watch it continuously. There's no like gaps or breaks. It's just. Great, thank you. So we don't find any effects of age here. We do have a limited age range. We expected maybe we should find some differences depending on amplitude or latency of these responses relative to age, but we didn't find any. And also, as a clue to where we're going, we did not also find any differences in the amplitude of the brain response depending on hearing loss. So already we're not finding something consistent with the Anu Sharma and Campbell and Julie Campbell paper where we see larger amplitudes at least, but a more interesting story is evolving with latency. So whether or not this N1 response happens earlier or later is the variability we're going to be looking at as it correlates to hearing loss or hearing thresholds. And here's what this looks like for the circle star stimulus, a big correlation of nothing, or at least very little. So along the x-axis here, this is the hearing thresholds, and what I've done here is I've adjusted it for age, so I'm partialing out age, and so we're looking at age-corrected hearing thresholds on the x-axis as our proxy of how much hearing loss there is. Higher values would mean more hearing loss. And on the y-axis is the latency of the visual evoked potential. And what we had hypothesized to find based upon past results is that those individuals with more hearing loss would have earlier brain responses, and we don't find that at all. What about that lip motion stimulus? Here's the correlation that we find. We find instead a sort of opposite correlation from what we expect, where those individuals with more hearing loss, what they have is more of a delayed latency for that lip reading stimulus. So we find correlations, but they are not very strong, and they are not in the direction that we expect here. And so this, to me, does not look like strong evidence of visual plasticity in age-related hearing loss as had been reported before. And I have been racking my brain to figure out, like, why is that the case? All of the hearing level that we measured between the two studies is matched. The visual evoked potentials were processed in the same way. I have the same latency ranges, and the stimulus presentation was all fixed here, but this does not seem like it replicates the result that we expected. And so we're left here with this idea that there's mixed evidence for whether or not there is some form of visual plasticity in age-related hearing loss. One small difference could be is our sample was slightly older, but not remarkably older. And I don't know if those age differences seem to matter. But right now we're sort of left with, we're trying to unpack this a little bit more. Maybe we can look at differences in mouth open, mouth closed. We also haven't done any analyses on alpha rhythms, which could be a novel insight into what's going on here. So this is sort of interesting. Maybe visual plastic effects are not that strong in age-related hearing loss. Maybe we need more severe hearing loss in order to see these effects. We'll see how these studies move forward. So to conclude what I'll be talking about today, I want to switch to some behavioral research that has happened in our lab. If we're not seeing these visual plastic effects, what about how individuals behaviorally use vision in order to help compensate for their hearing loss? And it's long been known, no secret, that being able to see a talker at the same time as listening to them improves your understanding of that speech. So there's a lot of redundant information for what the mouth is doing, what the articulators are shaping, can inform us for what kind of speech that we're hearing. And especially in noisy situations, being able to see a talker helps you with understanding the speech that you're hearing. Individuals with hearing loss particularly benefit from being able to see a talker, so they use visual information to help with their speech comprehension. It's been shown in several studies, and including some EEG studies by Sebastian Puschmann and colleagues. And also lower listening effort is something that happens by being able to see a talker. And what we'd like to know is that is how do visual benefits arise in these individuals? They clearly are benefiting from being able to see a talker at the same time, but if we know more about what is going on or how they're using visual features, then what we can do is encourage people to do those things more in order to reduce the burden of hearing loss. This may be especially helpful in cases where if somebody does decide to use a hearing aid, as they rehabilitate with their hearing aid, maybe we can direct them in proper ways to use visual information to act as a crutch for them to rehabilitate faster. So we're just trying to figure out how do visual benefits arise that we know that they happen, but what is going on. And there are several ways that could happen, and none of these are typically or could be considered mutually exclusive, but one obvious ask is, do they have enhanced multisensory integration? Are they leveraging visual information more and combining these things with the auditory information in order to perceive the speech better? And the evidence on this is sort of interesting. Most of the studies have focused on ye old McGurk effect. And in these studies, and if this is a new concept or something that you'd like a refresher on, the sort of a McGurk effect or a McGurk fusion is this perceptual illusion that happens when you have a mismatch between speech that you see and speech that you hear. So if I were to present to you an auditory clip of somebody saying the syllable ba, and then at the same time I present a video clip of somebody speaking, it's not the same sound, but they're speaking a different syllable, ga, what happens as you see and hear these things at the same time is a fusion of the two where your perception is the syllable da. And so this would be known as the McGurk effect, or this in particular is a McGurk fusion. And there have been a couple studies that have found that individuals with age-related hearing loss are more susceptible to the McGurk effect. That means they have a higher likelihood of experiencing a McGurk fusion compared to typical hearing individuals. How those studies are interpreted is that maybe people are relying more on what they see to help figure out what the auditory system is processing. If you have degraded information coming in from the ear due to hearing loss, they're more likely to rely on the visual system to resolve that, and so they're biased towards having a fusion of the two visual and auditory syllables. So that's sort of an interesting first line of evidence that, yeah, maybe they're more biased towards visual processing. There's also a much larger literature. There's a smaller literature on general auditory visual integration, both within speech and outside of speech in the hearing loss literature, and the results are quite mixed. The ones that best directly test for evidence of heightened or improved auditory visual integration, like they have higher amounts of additivity, or looking at the common ways that we look at audiovisual integration models, they don't really find any effects relative to age-related hearing loss. But at the same time, there's a much broader literature on auditory visual integration in aging. And somewhat of an issue with this large body of literature is that there's a confound between how old the individuals are and how much sensory loss that they have. What I mean by this is that about half of the studies, and how I know this information is from a really nice scoping review paper from Basharat and colleagues in 2023. This is Michael Barnett-Cohen's group from University of Waterloo, that only about half of the studies measure visual acuity. And I should have mentioned, we do measure visual acuity in all of our participants, and all of them are normal, but don't measure visual acuity, and about 2/3 of these studies don't measure hearing acuity or hearing level. And so it's hard to draw large conclusions across this body of literature because sensory loss and aging are confounded. So whether or not integration is contributing to these things, it could be there, but I don't have anything conclusive for you. On the flip side, another way that somebody could, or a person with age-related hearing loss could derive a visual benefit is from lip reading. Maybe there are better lip readers like we know in cochlear implant users, and we know that's the case in deaf individuals. This literature is also somewhat unclear, and I'll highlight one study by Nancy Ty Murray and colleagues. So in this study, why it's unclear is that they had three sort of conditions. They looked at lip reading for phonemes, lip reading for individual words, and lip reading for sentences. The only difference that they found between those people with hearing loss and those in control subjects was lip reading for words, but no differences in lip reading for phonemes and no differences in lip reading sentences. So they sort of were inconclusive about whether or not people with age-related hearing loss are better lip readers. So where does that leave us? So these are a couple of different things. So sort of what we had asked in the next question based upon these mixed results, and this was research led by Patricia Aguiar, is that maybe if it's not specifically lip reading, maybe they still have developed some sort of specialized processing for visual speech that can guide what they hear. So maybe they're using visual speech in order to, I can see what you're saying and I'll process that information, and then that helps me figure out or constrain what sort of auditory sounds are being produced from the talker. Another way we could, maybe it's not that, maybe a different way is that it's simply that I don't understand the speech coming into my ear, maybe it's a little bit degraded, and I'm just going to use visual information in order to resolve that uncertainty. And sort of to somewhat look at these two alternatives, Patricia derived this task to present auditory and visual speech separately. So she wanted to look at these outside of an integration-based task to see what was the influence of visual speech on auditory speech and vice versa. So the task that she had here was simply having a talker also saying a monosyllabic word, so not too different from what I'd shown you in cochlear implant users, where visual speech is presented first, then auditory speech is presented second after 1 second, or the inverse of that, where auditory speech is presented first and then visual speech. And the task was, are these speech utterances the same or different? It was hard to figure out how we could actually measure speech perception in this because the way the stimuli can interact. But we wanted to see if there were asymmetries in whether or not these visual speech presentations helped a person with hearing loss do this mismatch detection paradigm. And we had done this also in some background noise conditions where the speech, just the speech was presented in quiet. The speech was also presented at 0 dB SNR, so the level of the speech was the same level as the background noise, and the background noise is a multi-talker babble. It sounds like sitting in a cafeteria. And a more extreme condition of minus 10 dB SNR. So these are a situation where listening has no noise, quiet, and something in between, and also a very extreme noisy condition. Minus 10 dB SNR is a very difficult listening situation. So we did this study, this same different kind of paradigm for this configuration in 60 older adults, 35 women, 25 men, one person identified as gender fluid, and the age was from 60 to 81 years. We have a similar amount of hearing thresholds or hearing loss in this group as before, no hearing aids and devices. So let's jump into the results, and I'm going to present them all at once and then unpack them for you. So what we have, remember we have visual speech first and then auditory speech, and that's on the top row here, or the condition of auditory speech and visual speech. Across the x-axis, we have the hearing threshold, so the hearing loss is along the x-axis. Higher values mean more hearing loss. And along the y-axis, how we analyze these data, we're in a signal detection paradigm, so we're plotting D prime or sensitivity to detecting these mismatches, where higher values mean more sensitivity for the task. So we see a couple interesting things. Irrespective of the hearing loss level, we found that the performance on this task was better in the A to V conditions. So presenting auditory speech first and then visual speech, you're better at detecting those mismatches compared to the inverse condition. So that's kind of interesting. And there are also some effects that seem to change depending on the noise level, especially in the visual to auditory condition, that the higher the noise level, which are the different colors here, the purple is quiet, 0 dB SNR is in red here, and yellow is the very hard listening condition, in red, and then yellow is a very hard listening condition. And sensitivity seemed to decline with increasing amounts of noise. So that's cool. But here's what we noted. Notice how some of these functions change as hearing loss increases. Where those individuals in the A to V condition, when they had hearing loss, they did pretty well. But in the V to A condition, they seem to have performance decrements. And this is more what we would typically expect as a decline in performance with hearing loss. And what's interesting is that, especially in the 0 dB SNR condition, that sort of deficit was not erased, but it was mitigated. So if we take a simple difference score between these two things, we can see what sort of, I'm just calling it the visual benefit, and what I mean by that is how much better are they in the A to V condition compared to V to A condition, and that's what's plotted on the y-axis here as a simple difference. And the main finding here is that this mismatch detection benefit was larger in age-related hearing loss, especially in that medium noise condition. And so we sort of had two ideas originally when we started the study. Was presenting visual speech first going to help guide what somebody heard, or was the presentation of visual speech afterwards something that can just resolve that uncertainty? And when we compare those two alternatives, it's the latter explanation that we're more going on here. It doesn't seem like there's anything interesting or specialized about processing that visual speech first that helped out understanding auditory speech afterwards. And so it doesn't suggest to us that lip reading or visual speech has any sort of strong privilege. Maybe it's just there to provide some sort of benefit to resolve auditory uncertainty. And this case was most apparent when that auditory uncertainty included noise in addition to that hearing loss. It almost kind of looks like an inverse effectiveness kind of thing here, where the visual benefit is much larger in a level of noise. So to conclude, what we had talked about here today, at least in the second half, is that there's mixed evidence for visual plasticity and age-related hearing loss. At least in the results that we have, I'm not super convinced that there are these large visual plastic effects that we can observe, at least in our EEG study, for those stimuli. Maybe there are some stimulus-specific differences. We did see a sort of a positive correlation with the hearing loss level and the visual speech, but what that means has yet to be resolved. Speaking of resolving things, visual speech may help resolve auditory speech and age-related hearing loss. We thought there might be something privileged about visual speech, but it doesn't seem to come out that way in our results. Maybe it's just simply that people rely on vision in order to overcome the fact that listening can be difficult. And where we're going in the future here is to look at cognitive variables. We hadn't mentioned the idea of attention to visual speech or auditory speech, or also working memory for these things. So where we're moving towards in the future is we're going to do similar studies where we use eye tracking. We're going to try to see what facial features may be particularly helpful for individuals with age-related hearing loss, and to look at attentional modulation of also visual brain responses and differences that may deal with overt versus covert attention in those groups. And so with that, I'd like to thank you all for listening, and I'll welcome your questions if we have time.
Questions for Brandon?
I have a question about the age-related visual plasticity and why that might differ in your cochlear implant population. I mean, what's different about people who are getting older is their vision's deteriorating too,
Yes.
in many respects. So I'm wondering, they have a hard time seeing in many conditions. And so just this loss of all vision and hearing and tactile sensitivity, is that, why would you expect like one sense to take over if they're all going down?
Yeah, good question. It is. And just as a side, remember I did measure visual acuity, and all the participants all had corrected to normal vision if they didn't have normal vision. The comment here, and what's in the literature, is that the decline of hearing outpaces that of the decline of vision. So we don't see as much age-related vision loss as we do the extremes of age-related hearing loss. And so there's going to be an asymmetry in that loss. Would there be some sort of compensation that unfolds with that? The data suggested from the Campbell and Sharma study that, yeah, that could be the case, which excited us as a possibility. Just when we try it, we didn't find it.
I would just caution, like acuity and that sort of stuff, you see minimal effects of that, and there are a lot of other kinds of visual tasks, and sometimes you don't see any visual loss until after they're 70. But there are others, like useful field of view.
Useful field of view? Yeah, we write these down.
It's a lifelong deterioration from the time you're like 18, and it gets really bad. And that is used to guide all sorts of locomotive behavior. So it depends, just like I'm sure in hearing, it depends on how you measure it.
Yeah. So are there other tests you would recommend?
I have to think about it, but the useful field of view is something
Useful
that
field of view.
changes over the lifespan.
Right.
And you can find some people in their 60s and 70s that basically have tunnel vision.
Right,
So if they're
yeah.
attending to something in the phobia, they're essentially blind to everything that's happening in the periphery.
That's super useful because we have a bunch of hearing people working on this and not enough information from the visual folks, so thank you.
Thanks. I just have a couple of questions. I wanted to ask about, or maybe a comment, ask if you could maybe provide a little bit more context or clarity. In the case where you're seeing recruitment of visual responses in auditory areas, those areas normally do get some visual inputs, correct? You're seeing.
Oh, yes.
Right. Just want to make sure that people are not thinking that there's suddenly visual neurons spreading over from
No.
P1 into temporal lobe.
Yeah, I was going to try to be careful about how I was going to say these things. If you were to read the literature, you would be convinced from that there is visual reorganization of auditory cortex, or remapping, or even stealing cortical tissue. You see these very extreme versions suggesting that there are wholesale changes where computational units in auditory cortex are completely flipping their role to do something visual. And so this is some of the sensationalism that exists in the cross-modal plasticity literature. We do know already there are visual inputs to auditory cortex. There are also auditory inputs to visual cortex. These inputs are usually masked by the fact that those units are doing the intramodal sense operation. But if you were to lose that afferent drive, then all of a sudden those latent inputs become unmasked as they perform visual functions. So I'm a little agnostic on whether or not there's some sort of reorganization of these auditory areas. But really, if you lose your hearing, all of a sudden you have an opportunity for those existing visual inputs to become expressed or to upregulate. That's sort of...
Or to only be excited.
Or to only be
By
excited.
one stimulus.
Right. And so exactly, you see some of these things like map expansions or shifting around of the tonotopic map or other sort of regions or visual takeover or these other kind of things, but these probably represent existing inputs that are already there. And this has sort of been a recent debate in the cross-modal plasticity, in the stroke literature as well, whether or not using these terms such as reorganization or remapping are warranted.
Then your second concluding point about how visual information can help drive auditory. I'm just thinking, because we know that the sound localization, we know that the visual map of space puts the auditory map in register.
Yes.
Just from all the experiments with visual displacement and deafness, etc. So in a person, as you know, as they're aging or as they're in their task, they're basically looking straight ahead at the speaker's lips. So they're using their visual phobia. They're also using their auditory phobia. And I'm thinking that can nicely explain. They're actually getting the most benefit for hearing because their visual phobia is also, that's where the most responses are engaged. And I think that could help explain it. Because I wouldn't expect it the other way around, because we know that audition does not drive the visual spatial localization.
Right, exactly. One interesting things that we're observing, so we do have pilot data for eye tracking. Where are people with hearing loss looking at the face? They are looking at the eyes and the nose. And it might be more covert attention directed toward the lips. And this is also based upon anecdotal feedback I have from cochlear implant users, whether or not they're foveating on the mouth itself. And sure, they glance down there, but most of the time their fixation is on the eyes and nose, which is interesting. But they're still leveraging. Yeah. But we haven't noticed any remarkable changes where somebody is only looking at the mouth as a function of age-related hearing loss. More on that to come later
There's
on.
a study by Kevin Munhall that looks at the effect of McGurk depending on where they're looking, and it doesn't matter.
Yeah.
You look at the eyes and you'll get an equally large McGurk as if you look at the mouth.
Exactly. Yeah, that seems to track with what we're seeing too, and that's why we wanted to look at covert attention specifically. Maybe that's something that is improved in visual behaviors. Yeah. Is that someone else, Pat?
I just follow up on that point. I mean, Sarah, a former graduate student of mine, looked at face perception and how it changes with just the face discrimination task. And where you're looking, of course, doesn't necessarily imply what you're tending to.
Yep.
It's a different method for seeing what parts of the facial image are used in discrimination. And young observers, almost invariably, of North American observers, use stuff near the eyes, because that's where most of the signals information is. And older observers don't. They seem to have such a more diffuse, collect information more diffusely across the face. They're worse at face discrimination, but the idea is they're not just focusing on the eyes, at least in this simple face discrimination task. They use a less optimal, more diffuse things that also collects information around the mouth. And we thought that maybe it's because they're used to doing other tasks like trying to understand speech. There
Interesting.
is some evidence that, not based on eye movements, but just on if you manipulate the face a particular way. In younger people, manipulations around the eyes, that messes them up. In older people, manipulation around almost everything messes them up.
Huh.
They have more diffuse information.
That's also very useful for some of the studies that we're planning based upon masking parts of the face and seeing how that affects whether or not people with age-related hearing loss use those features.
Vision research, and actually maybe January.
Okay, well that'll be good for me to check out. Thank you.
So one difference also between the CI study and the age-related is the CI is people who have sought out devices to help with their hearing loss or deafness.
Yeah.
CI, and people who haven't. And so I do wonder if some of the results you're getting with the age-related hearing loss is you're looking at this subset of people with age-related hearing loss who at least perceive that they're coping without a hearing aid, and their performances, as you find the data, but people who perceive that they're not doing well and get hearing aids may be different because they at least self-recognize, or their family members or whoever says, get a hearing aid,
Right.
not coping well. And I mean, that's one possibility too about your differences between your study and this other study is that the social drives and availability of hearing aids, who gets hearing aids, how bad your hearing loss needs to be before you are driven to get hearing aids, they can be different in the different socioeconomic groups, different countries,
Oh, yeah.
things like that. So it may be that the cohort you have of people who haven't sought out hearing aid yet could be different from Anna Sharma's.
Yeah, it could be, and I don't. Hers weren't hearing aid users or anything. They were just recruited from their clinic. But the point stands is that if you're aware of your hearing loss, whether someone's told you or whether you're seeking help, maybe you're trying to accommodate yourself by using visual input more. And if you're unaware of your hearing loss, or maybe you reject that you do have it in aging, you are less likely to accommodate yourself. Maybe that could account for whether somebody adopts a novel visual behavior or not. Is that sort of like the same point? Yeah. Yeah.
But also, yeah, if you're only selecting people who don't yet have devices, those people could be different in different cohorts.
Certainly.
Across different countries, different socioeconomic groups.
Right. Yeah, no, all excellent points. These are all people from Toronto is who the sample was. Yeah.
In your second experiment with the lips opening and closing, you were looking at occipital electrode.
Yeah, we also tested other regions too.
Yeah, I'm just looking, I'm thinking about auditory cortex, because it's like a lip reading task, so you expect some activity in auditory cortex. And I was trying to understand that negativity you were talking about. And both of your like ah and have these continued phonemes.
Right.
And so maybe that's just a wash back from the auditory cortex is being activated, and that is then activating visual cortex.
Yeah, it could be like to explore what that actual negativity would be, or whether that we haven't looked at that specifically with the N1 response. We did try different sensor regions. We weren't set up as well to do source localization with the montage that we had, and neither was the former study. And so that's kind of why I was saying visual plasticity rather than saying whether it's coming from auditory cortex. We are planning a separate study in order to do combined EEG and FNIRS to look at responses coming from auditory regions.
Right.
So more to come on that, hopefully.
I have a question.
Yeah.
The cochlear implant group, they're very interesting for them to turn on a sense at some point in their life. And I wonder how much impact that has on their visual attention, because there's so much distraction now. They can hear things. And so do folks measure visual attention in these folks after this cochlear implant, before and after, to see if it's effective in some
For visual attention, not to my knowledge, actually. So it's very primitive visuals. Here's a visual event. We're going to measure the brain response, or here's some lip reading, or I was also looking at motion detection in the visual periphery, or things that they had looked at, but effects of attention not as well worked out as I'd like it to be, but that could be an interesting avenue to look at.
All the alpha fluctuations are also probably related to something with attention too.
Yes.
So now if you have this new sensory input, you have to suppress more, you have to pay the world and stuff, so I think there's something there.
There could be, and that's sort of the hand-wavy stuff that I put in the paper. Like we were trying to interpret what that alpha oscillations meant. We were drawing in some disparate forms of literature, but really not well theoretically developed. And so we need more experimentation, maybe manipulations of attention to better resolve that. Absolutely.
You have access to the CI patients soon after they get them?
After they get an implant? Yeah, we do. If they're willing to participate in studies, we can. At Sunnybrook, the clinic is right next to the laboratory. They can literally walk out of the door where they are dealing with the audiologist and come right into the laboratory. We can test them, which is a really cool setup. So we can very tightly time activation or the different time periods after they can come in with their appointments at specific milestones, and we can test them and track them longitudinally quite easily.
Very cool to try before and after with auditory and visual tasks.
Yeah.
To see if now once they got this thing turned on, how do they do on that same tasks before and after?
Yeah, excellent suggestion.
It's his idea.
So thank you, Brendan. Please join us for a reception on the second floor. But please join me in thanking Brendan.
Thank you. Appreciate it.